this set is x, this set is y, so you have a function f. If you take a set S here, which is of course non-empty, then you collect the integers of elements in the set. Fx1, fx2, etc. x1, x2, x3, and you make a set there. You are going forward. So this set is Fs. Fs has the expected meaning in the sense that Fs is all fx's such that x belongs to S. So F takes the set S to F, the set Fs. F takes x to Fx. Similarly, F takes the set S to Fs. So, as a result, we call it forward image of, I guess that's the word he is using, I noticed somewhere here. He has written forward image. Fs, the forward image of S, to distinguish it from the concept of the inverse image. F inverse S, we haven't defined it yet. But if F is 1 to 1, then you can talk of F inverse going back. Because if it is 1 to 1, if you take any y here, there is 1x here. Y matches to x. Function in a function, that is the property. Now, if you take any x here, there is 1fx. If it is 1 to 1, if you take any y here, there is 1x corresponding. So we talk about F inverse S, but we haven't defined it later. There is something, axiom of replacement, etc. Let's talk about that. I'm trying to make a little bit of a rush to get to analysis. If f n to n, the map fx equal 2x, then the forward image, it is clear now. Fx is 2x, f of 1, 2, 3, then 1 times 2, 2 times 2, 3 times 2, that's clear no? More informally, to compute fs, we take every element x of S and apply f to each element individually, and then put all the resulting objects together to form an M set. That's all. That's very clear. In the above example, the image had the same size as the original set, but sometimes image can be smaller because f is not 1 to 1. Here he has the function fx equals x squared. If you take the minus 1, 0, 1, 2, it has 4 elements. Since fx equals x squared, image of minus 1 plus 1 both are equal to 1. F of 2 is 0, f of 0 is 0. So here this side has 3, that side has less than 3, 2. It will, f of S has, it cannot have number of elements more than S. Less than or equal to, number of elements is less than or equal to this. Notice that f is not 1 to 1 because, notice that x belongs to S implies he says fx, the correct statement is, where am I? Y belongs to fs if and only if y is equal to fx for some x belongs to x. He's asking why, let's see why. This side, if y belongs to fs, then y must be equal to fx for some x belongs to s. That is the definition. No? If the other side is true, if y samana, if y is equal to fx for some x belongs to x, then definitely y belongs to fs. So it is if and only if. Now he is going to f inverse. F inverse. Here so far we had our S subset of x. Now we are going other way around. You have x here, you have y here, x, y. What is the set? He took u. He took u from here. Now, f is going this way now. This set may not be 1 to 1. It doesn't have a f inverse. To have an f inverse, it should be 1 to 1, otherwise you cannot go, no? But regardless of that, some elements matches to u. So that set we call F inverse U. F inverse U is set of all x in X, such that, as it yes, if X belongs to U, U is subset of Y, some elements of capital X goes to U under F. Images of some elements are in U. So this collection of all of them is called F inverse U. So just because of I wrote F inverse here doesn't imply that F is 1 to 1. Now there is a confusion. If F is 1 to 1, F inverse is a function, it has a meaning. Here, it is not that meaning. F inverse of U is collection of elements here which goes, the images are in U. So different meanings. Let's see, the F inverse U is the inverse image of U. Let's go. Here are some example. Let's go quickly. F n to n, fx equal to 2x, f of 1, 2, 3 is 2, 4, 6, no? That is clear. F inverse of 1, 2, 3. F inverse of 1, 2, let's drawing. No? Without drawing, you can talk about it. 1, 1, 2, 3, 1, 2, 3, yes. Here you have 1, 2, 3. Fx is 2x, no? 2x. Okay. Now we want to talk about F inverse 1, 2, 1. Sorry. 1, 2, 3 is right here. We are going to talk about F inverse of 1, 2, 3. F inverse parentheses braces 1, 2, 3. For that sets you have braces. So you are going to check what elements from here matches to the elements here. Fx equals 2x. Is there an element here when you multiply by 2, which is answer will be 1? No. Is there an element here when you multiply by 2 and just to hit some element here? Is there an element here when you multiply by 2, it is 1 or 2 or 3?
Yeah.
What is it? 1. So 1 is there. Right? Then is there any element here when you multiply it by 2 coming to 1, 2, 3 set? No. So that's all. F inverse of 1, 2, 3 is just 1. That's all. Because 2 comes as the image of, forward image of F. Forward image of 1, my English is incorrect. Forward image of 1 under F. F of 1 is 2, that's why it is here. So, thus the forward image of 1, 2, 3 and backwards image of 1, 2, 3 are quite different. Forward image of 1, 2, 3 is 2, 4, 6. Backward image or backwards image of 1, 2, 3 is just 1. Got it?
So what does that mean? F of f inverse x, we say 1, 2, 3 is not equal to 1, 2, 3.
Now, F inverse of 1, 2, 3 is 1.
Yes.
Therefore, Therefore, f inverse of set 1, 2, 3. F inverse of 1, 2, 3 is 1, singleton 1. So this is f of singleton 1. Fx is 2x. F of this set is, what is it? Fx is 2x. F of singleton 1 is fx is 2x. This is the definition. Remember, f of s is set of all fx such that x belongs to s. If you apply that definition, what will you get?
2x.
Eh? 2x. What is the only element here? 1. So, by definition, it should be f of 1. That's all. How much is f of 1?
2.
2. So that's why he said he hasn't computed f of this thing. F of that part is singleton 2. It is not equal to set consisting 1, 2, 3. This is why I am saying again and again, don't overlook anything little tiny. It's good that you ask the question. By doing that, you become a mathematician. Even if you are interested in a different subject, your mind will be carried away by the beauty. This way, maybe I don't have to write notes. No? If there is something wrong or I want to renew, then I can write. Otherwise, thing I don't like is separation, axiom, map, this and that. I don't know what they are. I have to read. Okay, informal. Then again we are talking here fx equals 2x here, x squared. Fx equals x squared is not 1 to 1, no? Because 1 and minus 1, both of them matches to 1. So, and 1 and minus 1 are different. Then f inverse of 0, 1, 4. What elements come to, let me now, new one, let's keep it over there. Who says here? X squared, fx equals x squared. So he wants to compute f inverse of parameter. Minus 1, 0, 1, 2. Minus 1, 0, 1, 2. Oh, where am I? This one, no? Yeah. 0, 1, 4. Bro. Silly. Silly. F inverse. So I want to check what are the elements going from here to 0. What are there any elements in this set which is going to 0? Fx equals x squared. I am asking whether are there sets whose square is 0. Are there elements here? When you square you get 0. Are there that kind of elements? 0. Are there elements here? When you square it, you get 1. What are they?
Minus
1 and minus 1. Are there elements here? When you square, you get 4. Minus 2 plus 2. So f inverse of, has it written it correct? Minus 2 minus 1, 0, 1. Right, no? F inverse of parenthesis 0, 1, 4 is equal to this set. So note that f does not have to be invertible in order to, for f inverse u to make sense. F inverse of whether or not f is 1 to 1 or it has injective, f inverse of a set is defined. F inverse of an element is defined only when f is, f inverse of a set is defined always. F inverse of an element is defined when f is invertible. F inverse of an element and f inverse of a set, we use the same word, but completely different meanings. Okay. Then f of is writing here f of minus 1, 0, 1, 2. Let's calculate quickly. F of set minus 1, 0, 1, 2 is f of minus 1, 0, 1, 2 is what? Fx is x squared. So f of minus 1 is this set is nothing but f of minus 1, f of 0, f of 1, f of 2. That's what it means. You apply f to every element in the set. Then f of minus 1 to the how much? 1. F of 0? 0. F of 1? 1. You don't need to write 1 again because it is already there. F of 2? 4. Right? Then f inverse of minus 1, f inverse of f of minus 1, 0, 1, 2. F inverse of the set minus 1, 0, 1, 2. Where on earth? No. F of minus 1, 0, 1, 2 is f of, no, f inverse of the set 1, 0, 4. Right? Because I have computed this 1, 0, 4. Now I am going to compute f inverse of 1, 0, 4. I have already done it. F inverse of 1, 0, 4 is, I guess, 0 minus 1 plus 1 minus 2 plus 2. So he is saying this set f inverse of f of this one is not equal to this one because this is the answer for that. 0 minus 1 plus 1 minus 2 plus 2 is not equal to the set minus 1, 0, 1, 2. The reason what he is trying to emphasize is if f is 1 to 1, let me do it again. If you take x, it goes to fx, right, under f. And if it is 1 to 1 by any chance, fx come back to under f inverse to x. So you may think when f is 1 to 1, f of f inverse of fx is equal to x. And when you have y here, f inverse of y, f of this thing is equal to y. This doesn't have to be true always. Can you see f inverse of f and f inverse of f, this set does not have to be the same set. It doesn't happen. That's why these are very little things we just spend couple of minutes. If the reason we have done, if f is a bijection, then we have defined f inverse in two slightly different ways, four sets only. But this is not an issue because both definitions are equivalent. You have to show if it is bijective, whether you compute, if it is bijective, you have a function called f inverse. Then you can compute f another one. And I always drawing it. See, let's take a S here. This is if f is 1 to 1, you can compute f inverse S because f inverse is a 1 to 1 function. Also, you can compute f inverse S whether or not f is regarding, whether it is 1 to 1 or not, you can always compute f inverse S. So, you have to prove that when f is 1 to 1, f inverse S has two different meanings. Even if f is not to 1, f inverse S has a meaning. When f is 1 to 1, even though you can compute f inverse S in two different ways, both are the same. Very easy one. So I am not going to write the proof on the board. Yes. No. මේ උඩු වාඩි වෙන්නම වෙනවනේ මට පැටි මේක ගණන් වලට වැඩි මේක අමාරු. ඔන්න. ඔය දෙන්නම. මම ගෙදරදී මේක කරනකොට කෑ ගහන්නේ කොහමයි වැඩි පුතේ හරි කවුරු හරි Okay, as remarked earlier, functions are not sets. However, we do consider functions to be a type of object, and in particular we should be able to consider set of functions. That's what I did, my functional analysis, you see. In particular, we should be able to consider the set of all functions from x, a set x to a set y. To do this, we need to introduce another axiom to set theory. Our axiom, yes, let x and y be sets. Then there exists a set denoted y to the power x, y to the x, like x squared, y to the x, which consists of all the functions from x to y. Thus, f belongs to y to the x, if and only f is a function from with domain x and range y. Power set axiom. It's a very important one. So, even though it is there, I also have to write at least once. At least once. X, Y are sets. Then x to the y, please go to y to the x. No? Y to the x is the set of all functions. This is set of all functions. Such that f is a function from x to y. F is the function from x to y. I wrote here, he has a different meaning, different words. F is a function with domain x and range y. If you are a fair person, you must be having a question. Why on earth we didn't write y to the x to the y? You may be thinking that. No? When f is a function from x to y, he has defined y to the x. Why not x to the y? You understand what I am saying? Why didn't he do so? So we have to answer that question also. Let's say, let x equals 4 to the 7. Also, I am sorry, 4 to the 7. 4 and set consisting 4 and 7. and y is the set consisting 0 and 1. Then y to the x consists of 4 functions. So let me do. Quickly. The x is 4, 7. Y is 0. So we are interested in functions from x to y. So let's define f1 first. f1, instead of writing f1 of 4, this and that, f1 of 4 goes to 0. 7 also goes to 0. This is one function. I am considering functions from x to y. f1 is like this. Then f2, 4 and 7, both goes to 1. I am considering functions from here to here. f3, 4 goes to 0, 7 goes to 1. f4, 4 goes to 1, 7 goes to 0. Are there any other functions? No. So y to the x thus, y to the x is f1, f2, f3, f4. Right? We have some more examples. No. Let's see what. And the function maps over to 1 and 0 to 1. The reason we use the notation y to the x to denote this set is that if y has n elements, bingo. Y has n elements and x has m elements, then one can show that y to the x has n to the m elements. In other words, if y to the x, the number of elements in y to the x is number of elements in y raised to the power number of elements in x. So that is why instead of writing x to the y, we wrote y to the x. That's the reason. Okay? So where am I now? Okay, the consequence of this axiom is let x be a set, then the set of all y such that y is a subset of x is a set. So it looks kind of funny, but you have to use the axiom, see it is a set, but in my case this is something taken for granted. How we read this also, the set of all y such that y is a subset of x. That's how we read, but he has many axioms, no replacement axiom, separation axiom, using them you need to prove. Remark, the set of all y is a subset of is known as the power set of x. 2. I have write that also. This duster is good somehow. Is this? Set of all y such that y is a subset of x is called the power set of x. Power set. In trains also you call it the power set, no something. It's a train going from Colombo to Jaffna somewhere. You say the power set is going. It's called the power set of x. Again, then you may have a question. Why so? Why use the power set? We have to answer that also. So, is known as the power set of x and is denoted. This is denoted, by the way. This is 2 to the x. 2 to the x. Set of all y such that y is subset of x. This is denoted 2 to the x. Then you may wonder why on earth 2 to the x, why not 3 to the x? So there are reasons. For instance, if A, B, C are different objects, let's do that. This is important. 2 to the A, B, C. Let's see. 2 to the singleton. Let's do A, B without jumping. Let's do 2 or 3 or 10. If A is an object, 2 to the singleton A is, so I have to write subsets of singleton A. What are subsets of singleton A? Give me one. Empty set, very good. Give me one more. A is not a set. Kuta? Singleton A. Now let's go to the AB. What are subsets of singleton? Set consisting A comma B. One of them? Empty set, very good. One more? Singleton A. One more, Buddha? Singleton B. Last one is set consisting AB. Now let's do one more very quickly. A, B, C. One subtest is empty set. One is singleton A, one more is singleton B, one more is singleton C, one more is singleton, pair set AB, other pair set is AZ, other pair set is BZ. Next one is set consisting all the elements A, B, C. Now you see why we wrote 2 to the x. When you have 1, you have to, this one has 2 to the 1. When you have 2, this one has 2 to the 2 elements. When you have 3, you have 2 to the 3 elements. And this is your homework for you to prove that if this one has n, it has 2 to the n elements. That's the reason. Time is flying now. I thought of doing so much today, but not enough time.
Get the cursor down.
Where is this here? Here. Now I am learning something. But did I do a mistake?
No.
Clear to you, no? Okay, Buddha, it says for sake of completeness, let us now add one further axiom. This is the axiom, union. I did not read from the paragraph carefully. Let capital A be a set of all of whose elements are themselves sets. This capital A, if you look at every member of capital A, itself is a set. Then there exists a set, union A, that's how we write. Whose elements are precisely those objects which are elements of A. Because every element of A is a set, no? Then union A is elements of A. Thus for all objects, X belongs to union A, if and only if X belongs to S, for some S belongs to A. That's important one. No? I don't write it, it's not that deep, but that's correct one. Yes. That makes sense only when capital A is a set of sets. Otherwise you cannot write such a thing. If capital A is consisting, this set contains only the sets. Set consisting 2, 3, set consisting 3, 4, set consisting 4, 5. Then union A is, you have to get 2, 3 from here. Here you have already written 3, you have 4. Then from here you get 5, 2, 3, 4, 5. That is union. Asking why, it goes without saying. But you cannot write. And the axiom of union combined with the axiom of pair set implies the axiom of pairwise union. Another important consequence of axiom is that if one has some set I, and for every element alpha belongs to I, we have some set A alpha, then we can form the union set U alpha alpha belongs to I, A alpha by defining. That's also very important, so I have to write. I have to write that here. Okay, now you understood this very well. Very well you understood. Actually, now when I write this way, if we write A, when we write A, this is like 1, 2, 3. But if you want to write a set, it contains singleton 1, set consisting 1, 2, set consisting 2, 4, 5. We usually don't write capital A. We write script A to make sure that as soon as you see it, you know it is a set of sets. So union script A is then 1, 2, 4, 5. Right? He is writing capital A. Anyway, doesn't matter. But these people know so much of English, not like us. But anyway, now can you see here union A alpha? Union A alpha, alpha belongs to I. This is A alpha, alpha belongs to I. He says this is union of union A alpha, alpha belongs to I. I mean, this is very clear here. Union A alpha, alpha belongs to I means take the union of all the sets like here. That's what it means, nothing else. But this is one way of writing union A alpha, alpha belongs to I. You get this kind of things so much, so don't need to worry about it too much. Which is the set thanks to axiom of replacement. See, these are the ones I am uncomfortable. Axiom of replacement and the axiom of union. I mean, these are actually not axioms. No, we know that. Even grade O-level students know the union. Let's see. This is a good example just to explain. Thus, for instance, if I is 1, 2, 3, let me do something else. Maybe I wrote something else here in my notes, but doesn't matter. Suppose I is equal to, say, okay, 1, 2, 3. Not 1, 2, 3, say A, B, C. I wrote, I think, a nice one. Nice one. Nice 1, 2, 3, 4. Okay, I have written this. One, two, three, four. My capital I is this. Then I have sets. A1. To me it is easy. Yeah, very simple, but just to understand the notation. I have written 26, 27. A2 is 36, 37. Just to clarify the thing, A3 is 46, 47. And A4 is 56, 57. And A5 is 66, 67. And maybe there may be some more. But I want to write I is only 1, 2, 3, 4 set consisting. Then union A alpha. Alpha belongs to I. Can you see here? I is 1, 2, 3, 4. This A of right. So I have to take this is union A1, A2, A3, A4. Right? Union A1, A2, A3, A4, 26, 27, 36, 37, 46, 47, and 56, 57. That's the union. A5, even though I wrote here, is not in I. Number 5 is not in the set type. So that's the meaning. These are not difficult. I mean, just to understand the notations. You need to be very clear about this, however. Then there is an important statement. It says Y belongs to union A alpha, alpha belongs to I. If and only if Y belongs to A alpha for some alpha belongs to I. So I am not writing it on the board because it is over there, but it's very important. Y belongs to the union means Y belongs to A alpha for some alpha. That's what it means. In situations like this, we often refer to I as an index set. That's the reason index begins from capital I. Capital I is called an index set. So you get index sets in analysis, algebra, so much sooner or later. And the elements of the alpha of this index set as labels. Yeah. The sets A alpha are called family of sets. Sets A alpha, we call it a family now. For instance, we call a family our family this and that, but here sets A alpha are then called a family of sets and are indexed by the labels alpha belongs to I. Read it twice, just keep in mind. Not that if I was empty, then union A alpha belongs to I would automatically also be empty. If I is empty, nothing to take the union. So when you take the union, you have to write the braces first, then you have to write the members, nothing to write, so it is empty. Now we similarly are going to define, we can similarly form intersections of families of sets. as long as the index set is non-empty. However, in this case, index set must be non-empty. For the union, it can be empty. For the intersection, index set must be non-empty. More specifically, given in a non-empty set capital I and given an assignment of a set A alpha to which each alpha belongs to I, we can define the intersection A alpha belongs to I, A alpha, by first choosing, and I don't know why he did like this anyway, it's fun. He says, I don't understand why he did this. A alpha belongs to I. I am writing because he has done it. What he does is, first he chooses one element beta of I. I don't know why he did this way. I don't know. Somehow we have to take the intersection, we are going to define the intersection of A alpha belongs to I. So what he says is, he chooses an element beta of I, which we can do since I is non-empty. Since I is non-empty, there is something there. Then he says, this is set of all x belongs to A alpha, such that x belongs to A, sorry, I didn't write the beta in. X belongs to A alpha. All alpha belongs to I don't know whether I'm rushing. You understand what I'm doing, no? So, when you are taking the union A alpha belongs to I can be an empty set. Because if it is empty, union is also empty. But when you are taking intersection, I must be non-empty. So, intersection of A alpha, this is the first book I saw this way. You know, you will be doing this thing 1,000 million times before you finish this course. Union A alpha belongs to I. He defines, he chooses some beta belongs to I because beta is non-empty. I is non-empty, you can choose. Then he is saying all x belongs to A beta, however such that x belongs to A alpha for all alpha belongs to I. You choose one beta, then you collect all the x's belongs to A beta, such that x must belong to A alpha, or all alpha belongs to I. And important thing is, I didn't understand why he did so, I didn't think about it. Maybe next day I will think about it and let you know. Which is said by axiom of specification. I guess maybe he wants to justify that axiom of specification that I haven't paid much attention. This definition may look like it depends on the choice of beta. Somebody may think it depends on the choice of beta, but it does not. Observe that for any object y belongs to A alpha, alpha belongs to I. If and only if y belongs to A alpha, alpha belongs to I. I am still wondering, I cannot answer you, why did not he define this way? To begin with. Intersection of A alpha, no, over there. Say, if you have two sets, y belongs to A intersection B, means y belongs to A and y belongs to B. Even if we have a family of sets, it must be the case. No? So he wrote over there, and he says, observe that for any object y. I mean, that is how, you see what I am saying?
The second way is more clear and
Yeah. Why on earth make it difficult something, no? Make you work harder. You have enough homework to do. And anyway, then let's go to read this one. The axioms of set theory that we have introduced. Dangerous one was that, which one we did not do? Russell's paradox. Are known as the Zermelo-Fraenkel axiom of set theory. That is the name of a set theory that we are using after Ernest Zermelo, 1953, he died, and Abraham Frankel, he died in 65. There is one further axiom we will eventually need, the famous axiom of choice. Axiom of choice is the most famous and most difficult one, I guess, to this day, giving the rise to the sermon of Frankel choice, ZFC, axiom of set theory, but we will not need this axiom for some time. Anyway, that's what he says. So the set theory we are doing is this Sermolo-Frankel axioms. When you are in analysis, except for highly abstract examples, you don't need it. But axiom of choice, I told you you need it, the measure theory subject that we are going to study. This book, I guess, does not have measure theory. This is in the other book. If he teaches you, okay, later. Anyway, so there is a bunch of exercises here. I went through them. They are not that difficult, but you have to do them. What is the next thing? Cartesian products. Okay, we come to Cartesian products. I guess today we are a little faster than the other days. Are we? I hope so, because we have to do a lot now. Plus, I should enjoy doing it, because when it comes to analysis, I really like it. It's very logical. So doing it fun. Cartesian products, you know Cartesian plane, XY plane, no? Cartesian products is something, two words are well known to you. In addition to the basic operations of union, intersection and differentiating, another fundamental operation on stress is that of the Cartesian product. Ordered pair, if x and y are any objects, possibly equal, we define the ordered pair xy to be a new object. Now we are considering x comma y is something new. That's what it is. Consisting of x as its first component and y as its second component. Two ordered pair x comma y and x dash y dash are considered equal if and only if both their components are matched. Components match, that is xy equals x dash y dash if and only if x is equal to x dash and y is equal to y dash. So that is the definition. This obeys usual axioms of equality. There are axioms, no? Thus for instance, the pair 3, 5 is equal to the pair 2 plus 1 is 3, 3 plus 2 is 5, you can see that, but it is distinct from the pairs 3, 5 cannot be equal to 5, 3, it cannot be equal to 3, 3 and as well as 2, 5. This is in contrast to sets, because sets are unordered collection of elements. Here, ordered. This is, you can change the order, no? Ordered pair, order is important. Sets, order is redundant. Strictly speaking, let's see. Let's go. There is almost 24 minutes. Something that I have written. Ordered pair we discuss. Strictly speaking, the definition is partly an axiom because we have simply postulated that given any two objects x and y, that an object of the form xy exists. We are postulating like an axiom. However, it is possible to define an ordered pair using the axioms of set theory. You may get the definition using axiom of set theory. Here, you know, intuitively one can ask, but in his case he has some axioms, no? Why x comma y? Why like that? What is the meaning? So there is a meaning to this. This says that using set theory you can define. However, it is possible to define an ordered pair using axioms of set theory in such a way that we do not need any further postulates. There is a way. For only ordered pair we will define and we will say it is well defined and everything. But when you have more than two coordinates, I am not going to define. That's too abstract, because we are more interested in learning concepts in analysis. Actually, in any subject there are useful things and useless things. For instance, suppose we are going to a dinner or lunch, then whether or not there are flowers, sent bottles in the table, I mean, they are redundant for us. We want to eat, right? Yeah, it is like that. Flowering things. Yeah, anyway. Strictly speaking, we have now overloaded the parenthesis symbol. We have used so many times. Once again, they now are not only used to denote grouping of operators and arguments of functions, but also to enclose ordered pairs. Now we use parentheses to enclose ordered pairs. This is usually not a problem in practice, as one can still determine what usage the symbols were intended from the context. Anyway, we are going to the point that we want to Cartesian product. Cartesian is the name of the person. If x and y are sets, then we define the Cartesian product x plus y to be the collection of ordered pairs whose first component lies in x and second component lies in y. Thus, x cross y again a set of all x, y, such that x belongs to x and y belongs to y. Though I don't write it, it doesn't matter, no. Even if I write, you are not writing, no, unless you copy it. So here you can copy it from the book. Actually, can you see that x and y must be non-empty sets in order to define, no? He hasn't said, equivalently, alpha belongs to x cross y, alpha is an element, then alpha must be something of the form x comma y, ordered pair, for some x in x and y in y. X cross y, any member of x cross y is an ordered pair whose first component is in x and the second component is in y. That's what it says. No? Remark 3, we shall simply assume that notion of ordered pair is such that whenever x and y are sets, Cartesian product x y is also a set. This is, however, not a problem in practice, he says. Can you see here we have taken, I don't need to write it on the board, I guess this time it is clear. If x is 1, 2 and y is 3, 4, 5, then x cross y is, first you take x, you take from x 1. Then with 1 you can take the three coordinates 3, 4, 5. Can you see 1, 3, 1, 4, 1, 5. Then you take the first coordinate from x, which is 2, then 2, 3, 2, 4, 2, 5. It is clear, no? And y cross x, then you take y, first one is 3, 3, 1, 3, 3, 1, 4, 1, 5, 1. You take first coordinate from y, 3, 4, 5, you took. Then x coordinate, second coordinate comes from x, you took 1. Then again you took first coordinate from y, 3, 4, 5. Then the second coordinate comes from x, which is 2. So you can see from here, x cross y and y cross x in general are different sets. However, they are very similar, in many ways. For instance, they always have the same number of elements. It is again an exercise. Here this paragraph is, it says quite a lot of things. I don't know whether there is anything big to define, but let's, because of last thing, let's say f cross y is said be x cross y is said be a function whose domain x cross y is a Cartesian product of two other sets x and y, then f can either be thought of as a function of one variable mapping in the single infotap ordered pair xy. When you have a function from x cross y to z, one can think this as a function of one variable, f of x cross y. and output is f of xy anyway. Or as a function of two variables mapping. One can think again it is a two variable because you have to let us x and y variables to a single output xy. So it is how you interpret. You can say it is a function of one variable if you wish, or you can say it is a function of two variables, but quite often it is useful to say it is a function of two variables because actually you have two variables, no x and y. But said theoretically it can be say, one variable because though xy changes, they are element of x cross y. While the two notions are technically different, we will not bother to distinguish the two and think of f simultaneously as a function of one variable with the domain x cross y and as a function of two variables with domain x and y. We think both ways. We are not going to talk too much about. Thus, for instance, the addition operation passed on the natural numbers can now be reinterpreted as function. Oh, because of that, which pen I use? This one. Now, from the n cross n cross n to n. You can say now you have n cross n to n. You have a function plus. Plus goes from here to there. Plus of xy is x plus y. You can consider plus as a function going from n cross n to n. So he has written it very carefully, defined by, he says xy goes to x plus y. That is true, but this is the actual thing. My function is f of, what is the object? X comma y. What is the result? X plus y. So one can say this is xy goes to x plus y. That is correct. Then what? Without sitting, I cannot read this thing because these spectacles, they move a lot. One can, of course, generalize the concept of ordered pairs to ordered triples, ordered quadruples, etc. Okay, now, ordered n-tuple and n-fold Cartesian product. So now, we have ordered pair. Pair means two, but it can be 3, 4, 5 now. We are living in the world of, usually we say, three-dimensional world, no? R3, no? That's how we say. Ordered n-tuple and n-fold Cartesian product. Let n be a natural number and ordered n-tuple. Here should be. Ordered n-tuple. This one can write this way, but this is the familiar one. x1, x2 up to xn. We call it n-tuple. N-T-U-P-L-E. It's a collection of objects xi. One for every natural number I between 1 and n. We refer to xi as the ith component of the ordered n-tuple. So this is called this is an ordered n-tuple. x1 is x1, x2 up to xn. x1 is the ith component, x1 is the first component, x2 is the second component, and so on. Because it is an ordered n-tuple, you cannot shuffle like in set. We refer to xi as ith component of the ordered n-tuple. Two ordered n-tuples. Usually this one is the simpler one for us. But one can write this way also. Two n-tuples xi, I between 1 and n, and yi, I between 1 and n are said to be equal if and only if xi equals yi for all I between 1 and n. If capital Xi, now it is a set, I going 1 to n is an ordered n-tuple of sets. Now it is ordered n-tuple of sets. We define their Cartesian product. You have x1, x2 up to xn. these assets. Then you define this product. You know this sigma sign is addition. This is production. I 1 less than or equal to I less than or equal to n xi. Actually, this is, one can write this way also, x1 cross x2 cross x3. Sorry, you don't need that much. 2 is enough. Cross xn is what? He says is an ordered n-tuple of sets. We define their Cartesian product, also denoted this way or that way by, I have to go here. I was trying to look at it. Same way, like what you expected. This is, you can write if you want, set of all x1, x2, xn, such that x1 belongs to x1, x2 belongs to x2, and so on, xn belongs to xn. Or you can rewrite the same thing. There are several ways of writing x1, x2 up to xn, such that xi belongs to capital xi 1 less than or equal to I less than or equal to n, and sometimes they write xi 1 less than or equal to I less than or equal to n, such that xi belongs to capital xi. I get to one. You can write in any way. That's several ways of writing. So, again, this definition simply postulates that an ordered n-tuple and a Cartesian product always exist when needed, but using the axiom of set theory, one can explicitly construct these objects. I did not pay attention to that kind of thing. Axiom 3.5.8. One can show that is indeed the set. So you have to, I have to look at the definition of a set here, because in my case I have taken it for granted, but in this course one shouldn't do that. Indeed, from power set axiom we can consider the set of all functions. Now our functions I going to xi from the domain 1 less than or equal to I less than or equal to the image, sorry, to the range. This can be considered as considered as set of all functions. Now you know y to the x is set of all functions. F is the function from x to y. Similarly, this one can be interpreted as set of all functions f going from, f is a function going from 1 to n to union xi, such that fi belongs to xi 1 less than or equal to I. You can think of that way also. It does not make any difference, but one can think of that way because we have this definition as a result. We can interpret it this way also. f of 1 is x1, f of 2 is x2. Like that you can interpret. That's what it says. They are not that, mathematics wise they are not that important. Example, this is again clear. If you have A1, B1, A2, B2, A3, B3, B objects, upper times lower, and let x1 equals ordered pair, since pair set A1, B1, x2 is pair set A2, B2, and x3 is A3, B3. Then we have x1 cross x2 cross s3. You can understand, no? That's correct. Then second one, x1 cross x2, then cross x3, x1 cross 2, x2 have a1, a2, a1, b2, a2, b1, a2, b2. So then you have x1 cross x2, cross x3, like, understand, no? Then x1 cross x2 cross x3 the similar way. Thus, strictly speaking, he says x1 cross x2 cross x3 and x1 cross x2 cross x3 and x1 cross x2 cross 3 are different. Strictly speaking, they are different. However, they are clearly very related to each other. No, I mean, except for the parentheses, they are the same. For instance, there are no obvious bijections. There are obvious bijections between in two of the three sets. And it is common in practice to neglect their minor distinctions between these sets. And I cannot remember any place where this was important, this parenthesis thing. I cannot remember. That's a function f from x1 cross x2 cross x3 to y can be thought of as a function of one variable, x1, x2, x3, or function of three variables, x1, x2, x3, or as a function of, again, two variables, one is x1, other one is x2, x3, like that. There are many ways of interpreting. They are not that important, but we need to know that there are that sort of thing. An ordered n-tuple of objects also called an ordered sequence. Usually in maths people, when we say sequence, it is infinite. But this is also, some people say this, but they could talk about finite sequences. In analysis, you don't talk about finite sequences because in analysis, sequence is always infinite. But one can talk, no? It's no harm in talking, no? An ordered n-tuple, x1 up to xn of x, also called an ordered sequence of elements, or a finite sequence, that's the word came, for short. In chapter 5, we shall also introduce the very useful concept of an infinite sequence, which is very, two more times one more time very important in analysis. We are going to learn about it very real soon. If x is an object, then x is a one tuple. One tuple, so no big deal. No? Only thing is you are putting x within parentheses. When you take x object, no parentheses, one tuple, same x, you put parentheses around, which we shall identify with x itself. It's like x no except for the parentheses. Even though the two are strictly speaking not the same object, they are not the same strictly speaking, but roughly they are the same. Anyway, then if x1 is any set, then the Cartesian product 1 less than or equal to I less than or equal to 1, xi is just x1. You are taking Cartesian product x1, that's all. Is x1 y, nothing to ask. Also the empty Cartesian product 1 less than or equal to I less than or equal to 0. That's kind of a little funny because 1, this way 1 less than or equal to 0 you did, no? 1 less than or equal to I less than or equal to 0 gives not the empty set but rather the singleton set, because that consists of ordered pairs. So this set consists of ordered pairs, so you cannot write empty set. That set consists of empty pair. I don't know what it is. Empty pair.
Empty tuple.
Empty
tuple.
Empty tuple, yeah, empty tuple. Whose only element is yes, zero tuple it says. Also known as the empty tuple. It's very good you said so. Anyway, these are just names, no big deal. If n is a natural number, I couldn't do as much as I wanted today. If n is a natural number, we often write x to the n. We write x to the n when all of them are equal. If you have x n times, this is denoted by x to the n. You have the same set, x1, x2, xn, everyone is x. Xn over here it is equal to product. That symbol is product, by the way. Like sigma is for addition, this is for multiplication. 1 less than or equal to I less than or equal to n, x, so it's not xi plus x. Thus x1 is essentially the same set as x if we ignore the distinction between an object x and the one tuple x. x2 is Cartesian product of x cross x, like we say R2. R2 is R cross R. R3 is R cross R cross R, 3 times. Same thing, these are just, the set x0 is a singleton set. Again, it is within braces, you have 0 tuple or empty tuple. We can now generalize the single choice lemma to allow for multiple but finite number of choices. So I guess we should stop here because it's not difficult, but I should not rush. No? But we can talk about the proof if you want. Where am I? You have finite single choice you had, no? Single choice is if x is an unempty set, you can choose an x from that set. We proved it. So this is finite choice. When you have finitely many sets, you can choose one from each set. Then you have axiom of choice for infinitely many sets. That we cannot prove, but it is there, so we make it an axiom. As I told you, that is the result. We are here, otherwise we should not have met at the lunch Goldface Hotel. We are here because of axiom of choice actually, because modern analysis is the result of axiom of choice. Okay, so let's prove it then. Let n grand, let n greater than or equal to be a natural number, and for each natural number I between 1 and n, let xi be a non-empty set. Then there exists an n tuple xi such that xi belongs to xi for all I. In other words, each xi is non-empty. Then the set is also non-empty. This is what it says. What it says is that, am I very fast today? Do you understand what I said? And if I didn't ask him, because if I ask him whether he understood it or not, till next Sunday or Friday he will say yes. Because he wants to come to lunch. After that, things can be different. After that, what we did was single choice. Was actually if x is non-empty, then there exists x belongs to x, we proved it. Then finite choice is if xi is non-empty for 1 I between 1 and n, then find xi I going 1 to n, which is equal to x1 plus x2 plus bingo, plus xn. This is non-empty. That is finite choice. In other words, i.e., you can choose, there exists, maybe I will do it next day, I guess I'm rushing. x1 up to xn belongs to x1 plus x2 plus. That's what finite choice means. Single choice, if x is non-empty, you can choose one element from there. Finite choice is when if you have n non-empty sets, you can choose an element from x1 cross x2 cross and so on, etc. That is called finite choice. Let's do it next day. Okay.
Shall I stop the
Eh?
video? Shall I stop the video?
Okay.